Okay, thank you, Bu Luki. You are now proceeding another method, another approach to facing the real problems in physics or astrophysical. But before we discuss this method, imagine that you have this two-dimension internal nodes or mesh structure here. Which become bigger and bigger. The number of internal nodes become bigger and bigger, but also we facing the problems which need to be solved in 3 dimensions. So the dimension of problems and the dimension of and the number of internal nodes becomes more bigger and bigger. So another approach, instead of using finite difference, every points, every nodes, spatial node. Let's see these problems. By doing this approximation, we imagine a volume and we replacing the value at a node inside the volume by this integral equation. The word volume here doesn't need necessary restricted to 3 dimensions, but can also apply to 2 dimensions or in 1 dimension. You can see here the idea behind finite volume method is calculate the average value of function f. Now I use pen here. For 2 dimensions, we use the same analogy here. So the integral was double here. One to x variable, another to y variable. And the last in 3 dimensions, simply we rewrite this integral equation here. So this is the principle, the fundamental principle in this finite volume method. The very, very important concept for the implementation. By using this procedure, It means that if we have a terms, and here we have a function, so we supply this function to this average calculation in 3 dimensions, in 2 dimensions, or in 1 dimension. Not only the value of the function in a specific node, for example. So if we have one term in PDE, partial differential equation, we could approximate this terms computation, term calculation by this procedure. So I hope this give you a clear explanation for how to use this finite volume method. This is the interpretation of finite volume method here. Compare with another method. This is finite volume method for 1 dimension. In a finite difference method, for example, here, this is central difference, I think. We approximate the value of the function f here using another value at another node here. Or this is another example. But in finite volume method, we approximate the value of a function here, f at I node by doing integration from the Jackson node in the left and on the left and on the right here. The value of this calculation divided by the value of delta x is an approximate value of f at y at I at node I. For today, we will be use an example of PDE solver using finite volume method. Which I choose for pedagogical reason is useful for us today. Please refer to this website, and the hands-on is already uploaded in the Google Drive for today. And you can download from GitHub, and reading documentation in this homepage of C Python. Okay, for introducing another introduction to numerical methodology, an alternative method to approximate the continuous we approximate by particle approximation. For example, like here, why do we need SPH, smooth particle hydrodynamics? This method have some of the advantage listed here. Firstly, the SPH is best to simulating the complicated flows, for example, in a region where wave breaking is happened, or in star formation or very large change in density has happened, or in multi-phase phenomena in volcanic eruption, or in, for example, also in solar system, I think, collision of rocks, fragmentation. This is the brief procedure of SPH. Firstly, we have to replace the continuous by particles. It's different with grid-based method. In grid-based method, we approximate the continuous by assuming that there are infinite spatial node, indeed, in the continuous, but we have to select finite number of nodes. In SPH, we assume that we don't have to see that the continuous consists of infinite node, infinite function describing the problems, the astrophysical problems, for example. It was sufficient to replace the continuous by particles. Then we have to calculate forces. So in the original version, this SPH was introduced by an astronomer, Lucy, I think, in 1970, maybe 70. This is the second procedure. We calculate forces, and the next is follow the motion of particles. In principle, we construct the partial differential equation, or for example, in ordinary differential equation here, grade R here related to time t. And the next differential equation here, grade velocity, which summation, sum over, for example, index force here. Of course, this is force per volume, maybe. This is acceleration indeed. This is related maybe to pressure, or if we list here friction comes from viscosity or another external force, including gravity, for example. The pressure here need not only related to the pressure inside the size of the environment, but also maybe come from the surface of the environment. So this is would be very complicated. Once you have do this third procedure, you have to doing time evolution. So you have to proceed to next time step. So you have to update the arrangement of the particles. How many particles in the neighborhood of a specific particle, for example. So we're doing this in repeated step. We calculate forces in step 2, for example, and follow the motion, and so on and so on. This is the brief procedure of smooth particle hydrodynamics. Well, this is wrong arrow direction. I apologize. Forgive me. Which the word smooth means that some particles' properties are determined by taking an average over neighboring particles. So only the neighbor contribute to this average. The word particle here means the fluid is represented by a particle system. So we don't use the grid approach here. There are many empty space between this particle. Yeah. It possibly like that. The word hydrodynamics means we use the equation of dynamics for fluid. The word smooth also means that close particles should contribute more than a distant particle. So we here figure out the circle to a description of how the neighbor contribute to a particle, for example, here. And we have to be very sure that the neighbor here doesn't contribute or not giving contribution to this particle. So we need to use a weight function to calculate this procedure. The two main steps of this SPH, first is the kernel approximation using integral representation. We call this kernel sometimes in a book. It was called smoothing kernel function or smoothing function or kernel for short. If you read in the book about SPH using terms kernel, it means smoothing kernel function. And the next step is discretizing particle approximation, because the first step was continuous function. But in this method, we are doing, we have the list of the particles. So every time we are doing this calculation, we know the dynamics of every particle, and we follow every particle in every time step. By doing this, we call this a Lagrangian approach. We follow the particle. We are moving with the particles. Okay, this is two examples of kernel function. We call the center particle as particle of interest. Let's say this particle particle I, we use the index I, and another particle, the neighbor particle, particle J here, and H here is the smoothing length. By using this kernel function, we are quite sure that we have the guarantee that this is the list of the neighbor which contribute to the dynamics of particle I here, particle of interest. Not this particle or this particle, but all particles inside this circle, for example, inside this geometry. This is like, what is, I don't know. For more clear explanation of the key ideas of this SPH that we mentioned before, we set arbitrarily distributed particle, and we don't use grid base, or we don't define spatial grid. No connectivity of the particles is needed. But in the next, we calculate the forces of course. No connectivity doesn't mean that we don't calculate the forces. Number three, we use integral representation. We introduce kernel approximation. But because of the number of particles was a limited number, so we replacing the integral function, the integral with the procedure of summation. And the fifth, the particle approximation performed at each time step. We have to update every procedure, every calculation, including the list of the neighbor around particle of interest. So we have to considering this. We have to consider this computation need to be very powerful for implementing real simulation problems in astrophysics. And a very long software developed for this for doing this simulation using SPH. For example, a gadget 2. We should see that this is this software need to be setting up in good hardware environment. The sixth idea is about support domain. It must be sufficiently large, and particles can be assigned mass and become physical material particles. So we know that a particle has many properties instead of including mass and also the size of the particles. So be sure to define the support domain larger than this value, for example, the size of the particles. This is one consideration, of course. The seventh key, which I mentioned before, we follow the particles every time step. So we call this Lagrangian. And the last idea, because this is related to dynamics, hydrodynamics, so we expose the dynamics equation. What is the update value of the position? What is the update value of velocity? Of course, the acceleration contributed by many forces. Another keywords in SPH is about domain and influence. Support domain and influence domain. In the previous session, we used the terms nodes here, but in these nodes, there are no particles. If you look at a particle of interest, we could define a circle which define a domain of particle which have significant contribution to the dynamics of this particle. We call this support domain. If you look at a node here filled by a particle, we call this circle as influence domain. For an SPH approach, SPH method, support domain is equal to influence domain. For short here, support domain means neighborhood of a material point, particle. Influence domain is a neighborhood of a node here, but doesn't fill with particle. Okay, this is very important note here. Sometimes we need to supply another parameter, which is the kappa here, to redefine the length scale, smoothing length here, because some particle near the support domain here is not really close to the boundary. And of course, kappa, the maximum value of kappa equals 1. Let's assume that kappa equal 1 for now. Okay. Now we're approaching the simulation by list the particles. And for each particle, there are many properties for the particles, and we need to visualize the dynamics of these particle system. Every particles have mass, velocity, position, including initial position. What are forces contributing to the dynamics of the particles? The density inside smoothing length, the pressure, because we approach these problems using hydrodynamics. And maybe you wonder, color, why? Because we need to visualize especially in the boundary. We need to do rendering of the particle system. Look at the surface, for example. Some of the particles are moving up, some are moving down, or another complex motion. So we need to represent this dynamic system. We need to visualize this system, particle system, by using color, rendering to a snapshot or a movie or video. Let's assume for particle I, these properties. Now, this is the fundamental concept of SPH. We need to know about interpolant, basic interpolant. I suppose you know the delta function here. if we integrate this delta function from a range of infinite range minus infinity to infinity, the value of this integration is equals 1. And for a value or terms, for example, in the PDE, for a simple example, we use this value, for example, A at point R. The interpolant delta function here, we use the value of R at R is computed by this integral. Now, the next step is replacing the delta function by the kernel. As we mentioned before, that there are many properties for this kernel. A particle of interest, contributing particles, and a smoothing length. So for now, we compute the interpolation for the value of A here using kernel function. Here, by using the spatial variable R here. But we can do manipulation here. We put this fraction, this unity value, row here on position R, contributing particle here. But we can interpret here to a 3-dimension interpretation. So rho times dr here equivalent to mass, for example, mass of the particle J, contributing particle, okay, now the next step is approximating this integral calculation by listing finite number of particles, replacing rho dr here by m mass, and here is rho. So for a better in order to better expression, I used to write like this: mj on row j are j times w. Of course, here r minus r, g, and including smoothing length. So we use this value here as a prefix for our memory, how to express another calculation instead of a, for example. If we replace this a with b, so we replace this a with b. But before we write mg on row j, mj on row j. Now this is an example. For example, we need to calculate the value of row particle of interest named row in Ri here. So we put this value in the summation here, and now we know that now we know how to calculate row using basic interpolant in SPH method. Of course, we are facing many terms in partial differential equation, not only row, but also, for example, first time derivative of row, or maybe divergence of mass flux or energy. This is why we call this following particle, the dynamics of particle. So we list every contributing forces here in another or in another variable, which is acceleration from pressure, viscosity. As I mentioned before, if we add the viscosity, so this called Navier-Stokes. This is the basic principle and the goals of the methods. Now, how to set up this particle list? Let's choose particle of interest here, mi equals mn. During the simulation, we don't change the mass during simulation. we assume that every particles for this simulation have the same particle mass equal m. Here is the formula for calculating mass. I think it's very clear. Okay, we go back to the weighted averages. This is a factor from particle of interest to contributing particles. We have done calculating density, mass density, using a kernel function W. And this is an example of kernel function. In this session, I skip the discussion of what kind of kernel function would be in specific simulation, but here we can see that one of form of this function, maybe a kind of this function, exponential function, maybe exponent e to the power of minus x squared on h squared, for example. And of course, this is the smoothing length h. Please note that the grade W here because W in this picture non-negative, but the grade W here less than 0. Okay, please pay attention for this SPH method, because we have to spend the memory of computer to huge calculation and to save the memory and to how to store the order of byte of information in a specific order. We will be facing with huge memory management here, because every time step we have to do many density calculation, for example, for every particle. And we have to update neighbor list in every time step. So this is an advantage we have to pay to implement this method by using luxurious computation facility, I think. So for today, I don't deliver this SPH method for doing experiment, a simple experiment in short time today or short time during this IVC for 2 weeks, I think. We will be doing experiment using finite volume method, which I mentioned short before. But I intended this session to introduce this finite volume method because this is one of the important method proposed by an astronomer originally. And now the SPH method used in many area of application, including industry. Yeah, because the power of computation become more and more powerful. Now, this is what I mean by doing rendering for one of the goals of these simulations. We have to track the surface, but we can imagine how the particle neighbor near the surface, for example, here. By inspecting or by monitoring the deviation of density compared with, for example, inner particle here. We could be sure that this is near the surface of the particle, the space, the domain that define this astrophysical or physical problems. One of the properties of the particles is pressure, and for an example here, we can relate it, the pressure, to an adiabatic, for example, here, pressure related to density by sound speed as a coefficient here. Okay, this is a list of the property we mentioned before. Next, we have to focus on the forces. Of course, by understanding the dynamics, we can doing calculation of velocity and position. Okay, how do we do this average calculation, or another terms in PDE. We can rewrite the average, the value of A replaced by average value of A here. And we approximate this integral function by summation, sum over J here. Now we use this, let's say this prefix mj on row j times aj related to this average value, of course, times kernel function. Like this example for density. Another expression is the grade of A. So we principally swap this to notation, nabla and A here. We swap this notation, A nabla. Or here, grade square of A, we also swap this notation, A nabla square here. Grade square of kernel function. So now we call this messless method because we have a list of particles. We follow the particles. We shouldn't worry about an empty space before between the particles. Another expression for this approximation, if we use a combination of value of this average, for example, Z is of course maybe a variable or constant here. If for example Z here a variable, you can express this approximation. We are doing approximation by specify the value of Z here in a particle of interest I here. Okay, now let's look at motion, equation of motion. Okay, we pick some terms for the next slide. For example, the first term in right-hand side here, one on row grade P for clear explanation how to implement this approximation. There are another terms here, including external force and central force, I think, including gravity here. Okay, let's see the first term, how to approximate, how we come to this conclusion that if we are to average this value, note that this is a small case of P, and this is another big case of P. It's different. P here, and here is. Yes, you could inspect the dimension of this big P here by inspecting the unit physical units of these variables. And from here we use kernel function at the position Rij here, written by Wij for short. Of course, there is also smoothing length here. Now, the first term of the motion is about the pressure here. 1 on rho grad P, and we expand this grad of P on rho here. We would have two terms. First term is here minus the second term here. Please inspect this expansion of this grade of P on rho. Okay, for now, for first term on right hand side here, this is the first. We swap this notation. So we write this mj on rho j times pj on rho j times grade of Wij evaluated in particle of interest position. This is to make this average calculation related to particle of interest. For the second term, remember the note on the previous slide, we approximate another variable here by approximating the value of first variable on a particle of interest. So pi on rho I square here is put it here before summation, and grade rho here we swap nabla and rho here. Please remember here the grade is evaluated in particle of interest. So the sum of two terms here are the first term on the right hand side in this Navier-Stokes equation. Is here. So this is what it means. Okay. In principle, we have to check the factor analysis concept or factor analysis textbook on how to rearrange divergence operation, curl operation, grade operation, or another operation related to differential in higher order dimension. For the second term, here contributed by viscosity. For short, we could express this approximation by summation over J here, because we have two nabla here. So we evaluate this kernel function by applying grade square operation to this kernel function. And this is another form of velocity related to mu here and rho. This is another approach to doing average calculation. Of course, we could see similar dimension, physical dimension of this expression, mathematical expression, or physical dimension with the same meaning. This is the square of rho, and also this is the square of rho. For summary, the acceleration of a particle can now be written here. We have shown that for pressure components, the acceleration is approximated by a p value here, big P here, or big V here for viscosity, and so on for another force. Again, we have to remember that for each time step, we have to find a neighbor. Imagine that if you are in a particle, because you follow the particle, every time step you have to look at around how many neighbor do I have and store it in a list, and then you calculate density for each particle, calculate pressure, calculate all type of acceleration, and sum it up, and of course calculating the velocity and position. Okay, by using the same integration method. Now, the color property. As we mentioned before, we need to interpret the simulation more easily, in a way that we know what is going on in a boundary. Especially the position of the particle near the surface, what is the pressure, what is the force in surface. So we can do calculation to derive the velocity and the position. And maybe we code the factors of the velocity in a specific direction, for example, normal factors. We identified these directions related to a color, for example, and if this factor slightly to another direction, maybe we have the mechanism to change the color of this property of particle, the factors, the velocity factor of particles. Okay, for the last discussion of the session about an example of SPH software. This is a folder for setting up initial condition for using a gadget 2 By the way, now Gadget has version number 4. This is what I mentioned before, that it's very serious to consider the memory of the hardware you use. Is it a big Indian computer or a little Indian computer? For many of personal computer we use today, especially laptop, I think most of them are little Indian. Means that Gadget 2 here seriously manage the mechanism of ordering the information by order of the information for least significant byte in little Indian computers. This byte stored in least address memory. And for more significant in the big address memory. You can check this type of Indianness of your computer by shortcut in or command line using a Python program here. Only calling this package. Now, the last slide is about an example of visualizing the particle, smooth particle hydrodynamics from Khan Academy. Okay. You can check this. Let me click this. Okay. Now I'm contacting the server. The simulation, this visualization have 3 parameters: number of particles here, viscosity. For example, if we supply by viscosity, like viscosity in water, maybe 3 or maybe 1 or 2, or but for honey, for example, we have to increase this viscosity value. And it makes very different visualization. This is one of the important things we used to see in SPH simulation, the visualization. Okay, I'll stop here. Thank you.
Thank you, Dr. Irfan Hakim. So, is there any question from the participants? If you want to ask directly, you can raise your hand. Okay, if not, maybe I want to ask something, Dr. Irfan Hakim. When we use SPH, we use a kernel function. Is the kernel function have to be Gaussian, or we can also use other function than Gaussian?
Yeah, Gaussian function is one example, an example of this kernel function. There are many kernel function that I used to play in this SPH simulation, but I didn't mention in this session. There are many.
Okay, so there are possibility to
There are
use
many
function
possibilities.
than Gaussian.
Yeah, for kernel function.
Okay, thank you. I think SPH is very important in astronomy because many of astrophysical modeling or simulation is use SPH, right?
Yes, especially because it was proposed by an astronomer. You can check this in the history of SPH. And second, it is an alternative approach, alternative method to introduce to undergraduate student, I think, to know, to recognize another approach to solve astrophysical simulation, astrophysical modeling.
Okay, thank you very much, Dr. Irfan Hakim.
Thank you.
Any question? If not, I will close this session.
Yes, I'm sorry, I'm not checking. I have no time to check chat room.
Okay, no problem.
There are many notifications.
Okay, if not, I will close this session and we will meet again